Welcome to another edition of Machine Learning Made Simple. Today we're covering two main topics, both making headlines, YOLO-E and Agentic RAG. First, YOLO-E. This is the latest evolution of YOLO, which is an object detection model which can detect objects in real time through live streaming media like camera feeds or self-driving cars. And this marks a major shift in object detection because until now, YOLO models were limited to recognizing only what they have been explicitly trained on. It could detect objects that it has only seen during training. But with this new model, the zero-shot detection model, YOLO-E can now identify objects it has never seen before. And this unlocks new possibilities for real-time AI systems, automated inspections in factories, and even planetary explorations where the ability to detect unknown is crucial. And then we'll turn to the Agentic RAG. The Agentic RAG is a new version of RAG, and the RAG was really hyped in the late 2023 as a solution to AI hallucinations, but it really didn't quite live up to the expectation. Poor retrieval, irrelevant sources, and weak ranking really made it unreliable, and as a result, it kind of faded from the spotlight, but research had kept pushing in the background. Now with Agentic RAG, the new waves are starting again, and this time it looks like they have finally solved the issues that held Retrieval Augmented System back. But before we jump into how Agentic RAG works, and we need to have a better overview of the fundamentals of the RAG itself and where it started, where it failed, and how it has been evolving over the past 2 years. We have already covered agentic AI processes in the last few episodes. Check out the links below if you missed them. In the next episode, we'll bring this all together. We'll merge the agentic AI and RAG to explore how AI can not just retrieve knowledge but actively decide what to retrieve and how to use it. Today we are laying the groundwork for Agentic RAG, and this is something everyone who is interested in AI needs to know, or at least needs to have a basic understanding of. So stick around. Today we're going to talk about both of the object detection model and also RAG techniques. A new version of YOLO is out, and the big question is, what is new? YOLO has always been known for real-time object detection, capable of identifying objects at 23 frames per second or more, but until now it has been limited to very small set of predefined categories which it needs to see during its training phase. And that has been a limiting factor because you cannot detect objects that the model has not seen during the training phase. And that's where the YOLO-E has stepped in and is trying to change the game, because it's now boasting that it can detect objects that it might not have seen during the training phase. And it is going through that process in 3 different modalities, either through text-based detection or image-based detection, or without any explicit input. So let's break down that, what all that means. First, let's talk about the zero-shot inference. YOLO-E can now detect object which it has never explicitly trained to recognize. This is crucial because most object detection models do need to be trained on very specific data sets which are labeled, meaning they need to struggle with unseen objects. But YOLO-E is generalizing that completely, making it far more adaptable to real world scenarios, meaning it can recognize classes of objects it never seen before. This is fascinating. Imagine an agricultural drone flying over farmland and spotting signs of disease in crops. Even if it has never been trained on that specific kind of disease of the crops before, the drone can now identify that the crops are diseased in certain segments of the field, and then can help the farmers take quick action and prevent losses. Especially for automated farming, this is revolutionary. And then there is text prompted detection. The next level would be the text prompted detection. Here the model is given words like white hat, red hat, white car, sunglasses, mustache, tie, and it tries to find those objects in the image, just like Clip. You probably are familiar with Clip, where you can do a reverse image search just by words, and Clip goes and finds the similar images with the similar embeddings as the word that we are searching for. This is really powered by a variation of that called Rep RTA, which really fine-tunes how the model understands words without needing a huge language model. In fact, previously they had to encode those words by calling Clip or VIT, incorporating all those technology architecture of having the latent representation of the words and calculating the latent representation of the words in the model itself, so that it doesn't have to make those expensive, time-consuming calls to external large language models to have the latent representation sent back to them. So this could be used in digital asset management. Imagine a journalist searching an extensive media archive, and they can just simply type beach sunset or crowded street, and the system instantly retrieves the matching footage. So, and the next one is visual prompted detection, where a small red box highlights a reference object, say a red hat, and yellow E finds similar objects in the scene. So it has tremendous applications, especially in any kind of design or editing and photography. All of them are holding a sunflower, and you want to replace all the sunflowers by tulips. So you click one of the sunflowers and all the sunflowers would be selected at once, and then with one click you can replace all of them. There is a separate project that's also working on that, and we'll talk about that in a different video. But for now, that's one of the good use cases, that if you can detect one of the objects, you can detect all the similar objects in that scene. Even if it's a streaming data, you can do it in live. So for this feature, they use a separate architecture called semantic activated visual prompt encoder. So they use the visual prompts, which is in this case, let's say you are looking for a sunflower in a crowd, and it goes to the activation branch and looks for what neurons are activated. Then the semantic feature extraction branch extracts that and sees what similar neurons are activated in other areas of the image, and then selects those areas. This is done in a latent space, so this is very efficient and not very resource intensive. So as a use case, this is useful in industrial manufacturing. Say a factory worker marks a defective component in an image, and the system then methodically scans the entire assembly line for similar defects, and it can do that in real time. This is made possible by a new technology called LRPC, which really allows the model to detect new objects by learning broad general patterns. So let's quickly talk about LRPC. This is not something new, but this was there before. This is essentially region detection, and we talked about region detection in an earlier episodes, and I'll post the link for it. Region detection lies at the core of any kind of object detection model, because we first have to detect what region of the picture contains objects. So for example, if some part of the object contains cows, and some part of the object contains grass, and some part of the object contains fences, then we need to segregate those parts of the images and then see what kind of objects we're finding in each of those regions. So region detection is very important. So lazy region prompt contrast, this LRPC, is an evolution of that idea, where the region is detected, and then each region, now we need to extract what classes of objects are in that. So that lazy part is that lazily it classifies like cow. It throws out few different categories. It might be cow, it might be a horse, like we don't know, and then it fine tunes and figures out which are the most probable classes in that region. So that improves efficiency because it comes with as many possible classes as possible. Then imagine how we also perform as a human being, and when we look at an object from a distance, especially those optical illusion where you have an image looks like a horse from one direction and a cow from another direction. It's like that. So the lazy loading is the something like that. Assign as many classes as possible and slowly gradually refine it. It's slightly more complicated than that, but that's the basic idea. This could revolutionize autonomous exploration, especially on Mars, when the Mars rovers needs to make autonomous decisions while doing its explorations and identifying rock formations and potential hazards, because the communication between Mars and Earth takes, even with at the speed of light, takes around 6.5 minutes. So that's too late before the Mars rover falls into a ditch. So it can do some autonomous driving already, but this will really change the landscape, figuratively speaking, when the Mars rover can actually identify objects that it might not have seen before. And why does this matter? Because in real world application, whether it's farming, media retrieval, manufacturing, or space exploration, we don't always have the luxury of a predefined list of objects. Yellow E represents that major shift towards truly open world detection, where models can identify anything, anytime, with or without specific guidance. Alright, let's talk about RAG. Not the kind you use to wipe a table, but retrieval augmented generation. One of the biggest game changers in artificial intelligence. You probably heard that large language models, LLMs for short, sometimes make things up. They hallucinate. It sometimes happens because the LLMs don't actually know most of the things. They just generate responses based on statistical patterns in their training data. So how do we fix that? Enter the retrieval augmented generation. Instead of relying only on what the AI model was trained on, the RAG lets the model fetch real-time knowledge to improve its answers. Think of it like this. You ask a regular AI, what is the latest research on quantum computing? It might just make up a convincing answer if it doesn't know anything about quantum computing. With RAG, the model can actually retrieve live research papers, blog posts, or you can give it your own research and knowledge bases to ensure its response is based on real data. It has huge application, especially in legal settings or research settings where there is very niche data is not available publicly. For example, if you're a legal firm, you have very specific set of documents and you want to generate documents in line with that structure. You cannot find that data elsewhere, and the large language model cannot produce data that's like the data you have. So you use the retrieval augmented generation to augment the large language model to produce documents just like you have in the past. So you have to feed your data to the large language model using this retrieval augmented generation method. Sounds like a game changer, right? Well, in practice, it's kind of tricky. The core idea behind RAG is retrieve and then generate pipeline. First, the model retrieves relevant documents from a database or a search engine. Mostly it's a database. Sometimes it's called a vector database. And then it generates a response using that retrieve content. There is some finer details we are skipping right now. Now, this approach is widely used in AI-powered chatbots, enterprise knowledge assistants, and even medical or scientific research tools, and especially definitely in the legal field. But here is the problem. If the retrieval fails, the model will still hallucinate. And as we shall see, most RAG pipelines today struggle with bad retrieval even today, irrelevant information, and weak document ranking. Irrelevance is the main problem right now. It will fetch documents which are not totally irrelevant, and in fact, Perplexity AI really suffered with this for a while. And there are in fact many research papers which pointed out that Perplexity AI has that problem of relevance in the search results. In fact, Google was much better. Perplexity AI since has solved that problem. So today we're going to break it all down. We go through how RAG started, where it went wrong, and what's being done to fix it. So if keyword matching was the problem, what was the fix? In 2021, researchers came up with a new model called Contriver, which replaced the keyword-based retrieval mechanism and switched to something smarter, a dense retrieval mechanism. So what does that mean? So now the dense retrieval mechanism converts text into embeddings, a mathematical representation of meaning, and uses that to find a semantically similar document which is semantically similar to the query. So the BM25, the keyword retrieval mechanism, sees your query as a bunch of words and tries to find documents that contains those same words. The more keywords are stuffed in a document, the more relevant it will think the document is, even if the document is irrelevant. Contriver, or the dense retrieval mechanism, actually understands the meaning of your query and finds semantically similar documents. For example, if we ask who discovered black holes, while the keyword search will find a document which has a black hole written over in it 100 times, but it doesn't say anything about who discovered the black holes. But the contriver will know discovery and black holes, those meanings must be combined together to find a semantic latent understanding which can only be found in those documents that mentions the discovery of black holes. And it will find those documents, Einstein and Schwarzschild, whoever discovered the black holes, it will find those relevant documents. So this was a game changer. It allowed better research assistance like Semantic Scholar. If you use Semantic Scholar API, it's very good in searching research papers, not just keyword stuffing. You can keyword stuff as much as you want, but it can extract the right meaning, and those extra keywords will mean nothing. So it is also used for AI-powered code search, where finding similar code functions required understanding the logic, not just matching variable name. But Contriver was not perfect. It had no verification step. Just because a document was related didn't mean it actually answered the question. If the query was too vague, retrieval was still bad, and that was a common problem. People don't search well. Most people don't know how to prompt well, and even in those times, even now, most people don't search well. They probably use one or two keywords and who discovered black holes, and that's it. They don't give more detailed prompts. The more detailed prompts we give, the large language model gives better responses, and that's one of the problems. Most of the prompts that the LLM gets are way too vague. So in order to improve the generation process, the prompts need to be highly detailed, and that's where the Contriver could have improved. And the next step was actually that improvement over the Contriver, where the prompts were actually enhanced by fine-tuned large language model, and that's what we're going to talk about in the next segment. So dense retrieval is really good, but even that is not good enough if the user query is too vague. And that's one of the biggest problems of naive RAG, even with dense retrieval, is that user queries are often really vague for the retrieval to find any kind of good information. So if someone is asking, show me ways how I can use a black hole or a wormhole to traverse to a new universe, that might be way too vague to find the relevant documents. And someone doesn't need to have a PhD in physics in order to, or astrophysics in order to make that prompt more detailed. The retriever should be able to do that, and that's exactly what the Replug framework does. It trains or fine-tunes a small language model in order to enhance the user query into more structured and information-rich before retrieval even happens. For example, if someone asks, how can we use a black hole to traverse to another universe, a standard retriever might fail because it is too abstract. It will just find a few documents here and there about traversable universes and wormholes, but not really answer the question. The real answer would be much more detailed. So the Replug's query generator will take that query and refine it and make it more fine-tuned and rewrite it in something like retrieve all documents on charged black holes, including Reissner-Nordström solution, examining the Penrose diagrams, and then use it to find relevant references on how to use that to traverse those black holes or wormholes into another universe. Now that is a query that actually guides the retrieval towards useful resources and documents. And this is how it essentially works. The user submits a query. The query generator, which is a fine-tuned small language model, enhances this query to make it more precise, and the retriever then uses that enhanced query to search, and those top documents are now retrieved and passed on to a frozen downstream element or black box LLM like GPT, which can use those relevant documents to generate the final answer. If GPT doesn't have those information, it can now produce a more augmented answer because it has those answers. Now, of course, the new versions of GPT have all those answers anyways, but we're talking about pre-GPT 3.5, then where it struggled with all that information. So this was super useful for research tools, legal searches, especially legal searches, where all the legal documents might not be available because it might be very domain specific or even company specific. So all those fact-based chatbots, all those legalese, any situation where even a slightly off query could lead to totally useless results, that's where this comes in. Because if the retriever makes a tiny bit of mistake and if the documents were not there, it will totally fail. But there's still some weaknesses. It just generates a single refined query. So if the enhancement is wrong, if the fine-tuned LLM didn't enhance the query correctly, if it failed in understanding the intent of the user query, then the entire retrieval will still fail. So imagine the whole pipeline is now dependent on that single query generator, which may or may not work. So now there is a single point of failure, which can cost money every time that entire pipeline runs. So, and that's where RAG Fusion comes in, makes this process that was single point of failure and takes it out and replaces it with something more robust. And that's what we're going to talk about next. Alright, so Replug improved retrieval efficiency by enhancing user queries, but it also created a bottleneck because if it failed to understand the user intent, it might enhance the user query in a direction the user didn't intend to go. For example, if the user asks, tell me about Apple, and if the fine-tuned retrieval enhancer or the query enhancers misread the intent of the user, that the user is not really asking about the Apple iPhone, the phone, but it thinks that the user is asking about the apple fruit, then it will enhance the query explain to the user more about what the fruit apple is, its origins, and what are the different varieties. So you see just the question, the intent of the user is completely changed if the query enhancer misrepresents or misunderstands the user's intent. The one way to go around this is to create multiple queries or multiple enhanced queries, not just one enhanced query, and that would probably solve the problem. And that's exactly what the RAG Fusion does. It takes the Replug's approach further by generating multiple enhanced queries or multiple versions of the enhanced query, and then retrieves the documents separately for each of those enhanced queries, and then merges the most relevant results by using some kind of a ranking method. Think of it like running multiple Google searches with slightly different wording. Instead of just hoping that a single refined query gets everything right, the RAG Fusion diversifies the search and gathers more perspectives and then filters out the irrelevant documents before sending them to the LLM. User submits a query, the query generator produces multiple enhanced queries, each query retrieves a different set of top K documents, and the ranking method selects the most relevant document. And this ranking method is kind of advanced version of the TF-IDF. If you're interested, I did a video on that too. So this is particularly useful for really complex research topics, legal or medical searches, and also technical AI assistance. Any case where one way of phrasing a question might not be enough to retrieve all the relevant sources. But it's still not perfect. It is computationally very expensive because running multiple queries mean retrieving and ranking way more documents than actually is needed. And if the ranking mechanism is not fully tuned, then it might discard useful information. RAG Fusion is a major improvement in retrieval quality, but it's still not the most advanced approach today. Most recent methods like context-aware RAG, modular RAG, memory and augmented RAG, agentic RAG push retrieval away even further by adjusting retrieval in real time and integrating multiple retrieval sources dynamically, and we'll talk about that in a separate episode. So for now, we'll just mention this. In the next episode, we'll talk about more advanced versions of the RAG. Before we wrap this up, let's talk about the vector DB based RAG methods that we are still using. Many people said that they don't work or they're bad, and the reason is that those systems are still following the naive RAG method, and we actually mentioned it a few times during the course of this episode. Most modern RAG systems use vector databases, but does that mean they are still naive? Yes, vector databases like Pinecone and Vivian became the standard for RAG because they're fast, scalable, and easy to integrate. But here's the problem. They still don't guarantee good retrieval. Embeddings might retrieve similar content, but not necessarily the right answer. Chunking breaks up documents into smaller vector-sized pieces, losing important context, and that chunking is used a lot in these methods. And the top K retrieval is really arbitrary. The ranking mechanism is really arbitrary. In fact, if we see the RAG Fusion paper, their ranking method is much better because the top K retrieval method assumes that the correct document is in the top K results. And what if it's not? Let's look at Perplexity AI. Even though it uses top tier retrieval, it still struggles with irrelevant sources. Why? Because there is no post-retrieval validation. Vector databases might make retrieval faster, but they didn't necessarily make it smart. Unless we get better retrieval techniques, hallucinations will still be a problem. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.